Okay, welcome to the session number 2. Now I have the pleasure to present to K.Knuth from the University of Albany, and he will talk about quantity with uncertainty. He defines the physics of quantum mechanics and spacetime.
Right, great. Thank you for having me. Hello, everyone. And yes, I'm doing this. This work has been working on this with John Skilling from Ireland, and so we'll dive right in as long as everyone can see my screen here. So this work basically takes advantage of a slightly different perspective of what we are doing in physics. Instead of thinking about the natural laws, the laws of nature as being laws that are dictated by Mother Nature and that we all have to obey, we're looking at. I'm looking at this from a perspective of people wanting to quantify things, and we've gotten so used to quantifying things, and by that I mean assigning numbers to things, that we almost give it no additional thought. And of course, this is a very simple process. We learn to do this as children. We assign numbers for different properties of objects, and the larger things are typically assigned larger numbers. And of course, there's some arbitrariness here. There's some choice you can make. So here I have pictures of some batteries. 1.5 volt battery, a 6 volt battery, a 12 volt battery. And so we're assigning numbers to one aspect of this set of batteries. And classically, we tend to, because we're so familiar with this, we have come to think of these quantities as being properties of the objects themselves. So in fact, we even use them in the name. This is a 12 volt battery, and that's that number 12 is considered to be a property of the battery, which I think is that's a little too strong. And you can start to see where this is going to be problematic when we consider things like very small objects where the probes that we're using to study them are equally small. The assigned quantities in these cases really describe interactions rather than describing properties of the objects. So we often, our language often governs how we think, and how we think is described by our language. So these two things are coupled, and very often we'll hear people say, I myself will say things like, an electron has an energy E or has a momentum P, and that's really not a good way to think about it. The electron can't possess a momentum because the momentum of an electron is really observer dependent. You boost to another observer in a different frame, and they'll measure a different momentum for the object. They'll say, this electron has this momentum P. And of course, we know how these two numbers are related. But I think that one of the difficulties that we've faced conceptually is taking these numbers that we're assigning as descriptions of objects, descriptions of properties of objects, descriptions of the way that they're interacting with observers, and attributing them to being numbers describing properties of the objects. And that, I think that's really a wrong way of thinking, and it's caused us a good bit of trouble. The momentum and position and energy, these types of quantities really are describing the relationship between the electron and the observer. And so momentum is one description of the relationship. Position is a different description of that relationship. And the fact that the two descriptions are incommensurate really isn't surprising or unusual. They're just two different descriptions. And so there's been in quantum mechanics, historically, there's been a lot of puzzlement over the fact that how can an electron not have a definite position and a definite momentum at any given time? Well, the fact is the electron doesn't have either. Those are descriptions of the relationship between the electron and the observer. And you can't have both of those descriptions can't hold at the same time. That's really what's going on there. It's really only mysterious if you think of these quantities as properties. So we've worked hard to give up these ideas of properties and thinking of this more in terms of description. So contextuality in this case becomes a little less mysterious. The context of the details of the interaction matter. And of course, how you are going to describe an interaction depends on the details of those interactions. And descriptions need not be commensurate. You can have complementarity. The electron doesn't simultaneously possess a momentum and a position. The electron doesn't possess either. That's a bad way of thinking. So what this does is it gives you a bit of freedom, which is interesting, and the profitability of such a perspective then is measured by what it allows you to do, and we've found that it allows you to actually do quite a bit. So if you're going to assign numbers to objects or properties of objects or interactions between objects and probes or observers, then you need to do so consistently. And the question becomes, how does one consistently assign quantities? So different operators may have different frequencies may have different symmetries. And these symmetries can be quite important because they will constrain the number of ways in which you can assign numbers to things. So let's say I have two sets of candy taffy here, and I'm using candy because what I'm going to be doing with these taffy is rather simple. You've all known about this since you were kids. So I've got a set here A of some taffy, and I've got a set B of some taffy, and I'm going to combine the two. So let's say I have set A in one hand and set B in the other hand, and I'm going to put them together. Now, if I want to quantify these sets, basically assign numbers to the sets of taffy, one obvious way to do this that you're very familiar with is to count them. We'll assign a number describing the cardinality of the set. And one can then ask the question, well, how do you take the number that you assign to set A and the number that you assign to set B, and how do you combine those numbers to arrive at a consistent number that you're going to assign for set A with B? Of course, you all know the answer to this already. You add them. And my interest in this question came from the deeper question that I had in graduate school, which was, why do you add them? I know that it works. It's obvious that it works. I've been doing this since I was a kid. But why is that the case? Can you prove that it has to be that way? And indeed you can. There's several different properties that this with operator, basically combining stuff in two hands, exhibits. This combination property with exhibits closure in this case. So if I take stuff A and combine it with stuff B, the stuff that I have in A with B are the same kinds of stuff. If I take taffy in my left hand and taffy in my right hand and combine them, then I still have a bunch of taffy. So that's closure. Another symmetry that you have with this operator is the is commutativity. Doesn't matter which hand I have the set A of taffy in, which hand I use to pick up the sets in the first place. I could switch hands and I still have the same result when I combine them. That's a symmetry. If I have 3 piles of taffy and I start picking them up, I can pick them up in various ways and the result is equivalent. That's called associativity. And the idea is that the with operator is such that I can keep grabbing piles of taffy if I want. And so mathematically, I ought to be able to keep combining them. So these are the 4 conditions that the with operator has to satisfy. And you can prove, this is a theorem, you can prove that if the with operator satisfies these 4 conditions, and you can think of associative commutativity as just shuffling. I can shuffle up the piles and I get the same result. Then you can show that if you're going to quantify the set A with a number represented with lowercase a, and you're going to quantify the set B with a number given by lowercase b, then A with B is basically going to have to be quantified by something that's isomorphic to A plus B. And that's a theorem, and that's something you can prove. So you might say, great, that's something we've known this all along. Not very exciting. I've known this since I was 3 years old. But it turns out it's rather profound. And so here's the example. If I assign the number A, 3 to the set A, I assign 10 to set B. There's a little taffy hiding under this one. So now when I combine them, the number that I assigned to the set A with B is given by 3 plus 10, or 13. And that will give me a consistent means of quantifying these objects. So how well does this work in general? Well, it works pretty well in general. We use it all the time. We count all sorts of things, from taffy and rocks to gallons of gasoline to cars on the highway to stars in the sky. But let me give you an example where it doesn't quite work, because one might be led because of the generality of the application of the mathematics, you may be led to thinking that this is some kind of universal physical law. And it's not quite that simple. This is a description. I can emphasize the fact that it's a description by showing that it is observer dependent. So here's another example. I have 2 sets of objects. Each of these sets contains molecules. In the ones on the left, I have 2 butane molecules. And in the set on the right, I have 13 oxygen molecules. There, maybe this is in the way on my screen. So now I'm going to combine the 2. So on the left, I have 2 molecules. So I could assign, you can conceive of assigning this a number 2. On the right, I have 13 molecules. I give it the number 13, and I'm going to combine them. And you expect to have 15 molecules, which is nice. And that works as long as you don't shake this up and make it too hot. Once you make it too hot, this happens. And you no longer have 15, you have 18. And you have 18 carbon dioxide molecules and water molecules both. So what went wrong with our little rule of additivity? In this case, 2, it should be 2 plus, I have the numbers up here wrong, but our 2 plus 13 actually gives me 18. So why did that happen? What went wrong? The answer is quite simple. What went wrong is we violated one of the conditions for the with operator. The with operator lacks closure. You don't have the same kind of stuff at the end that you had in the beginning. So whether addition worked or not depended on our description. If I were to go back here to the beginning. And instead of counting out molecules, if I counted how many atoms I had, and here I have 4 times 2, which is 8, and then 10, and so it's 20. So I got 28 atoms on the left, and I have 26 atoms on the right. And now I throw them together and shake up the box. I still have the same number of atoms. You can add the number of atoms and you get the right result. So addition works if you count the atoms, but it doesn't work if you count the molecules. So that shows that there is a dependence on the level of description that you choose. So whether additivity works depends on the description you chose. And the laws of nature shouldn't depend on description if they're going to be some universal law. So this isn't about a law of nature. This is about describing things with numbers. So there, of course, there are other operations you can do. You can take 3 copies of the set A, and I'll call that 3 of A. So this is a new operator called of. I can replicate things, and it turns out this of operator is obeys associativity, and the of operator is distributes across the with operator. So you have distributivity. So here we have associativity and distributivity, and you can prove, again, similar to the proof before, the associativity means that the number that I assign to, so if I assign a number to, if I have this number A and I assign a number to B, little a and little b, then the number that I assign to A of B is going to have to be, it's going to be some function of little a and little b. And associativity forces that to be isomorphic to addition. But because we used addition for the with operator, the fact that we have distributivity forces that isomorphism to settle on one particular transform, which is basically multiplication. So multiplication is isomorphic to addition, so it satisfies the associativity, and the multiplication will satisfy distributivity. So this is a theorem. And so the idea is you multiply the numbers together. So now when I take 3 of A, if I assign a number 3 to A, kind of unfortunate I use 3 here, basically when I'm done, 3 of A is going to give me 3 times 3 or 9 pieces of taffy. And you can prove that this has to be the case because of associativity and distributivity. So these are rules for consistently quantifying numbers, or quantifying things with numbers. And now we're going to push this to an extreme. We're going to consider the case that we encounter in quantum mechanics, where we are studying very small objects with very small objects. There's a point where we get to where we are studying objects for which there are no smaller probes by which we can use to study these, and we may obtain some number x in a measurement, and which we would use to quantify this interaction, but we have to acknowledge that we're going to have some uncertainty as to the value of this assigned quantity x. You can also think of it this way: we have some quantity describing the system, some describing the probe. So you put the two together, you really need 2 numbers to describe the interaction between the system and the probe. Now this uncertainty, the relationship may be more intimate than the usual x plus or minus sigma uncertainty that we're used to from dealing with Gaussian probabilities and probability theory. And in fact, I would like to, in this case, if I did want to quantify things this way, I would have to derive this plus or minus as being a function relating these two. So to back up and work to do something like that, we're going to not assume that this is the case. Instead, we're going to assign 2 numbers here. One number is related to the a number quantifying the interaction x, and another is going to x1, say, and the other is going to be x2, which will quantify uncertainty. We just have two numbers here instead of one. So what happens when we consider similar operations like the with operator and the of operator, and we start combining things, and we are using two numbers to describe these interactions rather than just one? So we'll look at associative commutativity again, which previously with scalars in the Taffy gave us a sum rule. We find that that's the case here as well. So if we have some set A, something A that's described by two numbers x1 and x2, and then we have a B described by two numbers y1 and y2, then A with B, where this with operator is any operator that exhibits closure, associative commutativity, and reproducibility, then A with B has to be represented up to isomorphism by component-wise summation. So we would then assign for A with B, we would assign numbers x1 plus y1 as one number and x2 plus y2 as the second number. That's not so unusual because it's not so different than you can see the scalar case right there. Things get a little more interesting when you consider an additional operation like the of operator, where you have associative distributivity as well. So here, upon interaction, associative distributivity, which we'll use this operator as dot, is we're trying to figure out what dot would be. We will have distributivity here. We also have associativity, and we also have component-wise summation for the plus here, and that requires that this dot operation has to be bilinear. So whatever numbers x and y you have in the original pairs, the result is when you combine them is going to be some linear bilinear combination of these objects, where these gammas here are coefficients that we have to identify. So these basic symmetries are common in the systems that we work with, and that is why we use addition all of the time, because we have associative commutativity holds often, so addition works. And in physics, generally, we have associative commutativity and associative distributivity, and that is why physics is fundamentally linear. Excuse me. So now, whereas scalar quantification resulted in one multiplication rule, the pairwise quantification, where we're carrying with us a number quantifying some uncertainty, results in 3 multiplication rules, which is interesting. So, and that these come about from looking and seeing what gammas are possible. So it turns out that there are 3 sets of gammas that are possible, and all the different versions reduce to 3 different types of operations. One of these here, you'll see the first one, A, looks like complex multiplication. So you're basically treating these as complex numbers. And B is similar, but we have addition here, and C is also similar, but not the same. We can rewrite this as as a matrix operation, where A looks like this, B looks like that, and then we operate on the vector y1, y2. So these are the 3 different multiplicative operators that we have, and we will see that much of physics comes from these 3 operators. So without loss of generality, we set the determinant of these operators to 1, and we do that so that repeated application doesn't diverge to infinity or collapse to 0. That would be pointless. And that means that there's really only one free parameter related to the ratio of x2 to x1, which gives us three possibilities. We have something like a rotation matrix for multiplication rule A. We have something like a hyperbolic rotation for multiplication rule B. And we have this other matrix for operation C. Each of these three will obey those symmetries, so they may be useful in quantifying things in the real world that obey the symmetries, or interactions in the real world that obey the symmetries. So of course, we can write these operators in terms of infinitesimal generators. This is what the generators look like. And we then see that generator A is basically rotation by some phase angle, and which is what I had originally said. So there's a rotation matrix. So generator A basically rotates by a phase angle. And the sum and product rules in these cases are those of complex arithmetic, and the pairs are complex numbers. Unit quantities identified with unit modulus determinant, which is modulus squared. And we find that the inherent uncertainty in a unit object refers to what remains unidentified in X, which is namely the phase, this rotation, so that every time we have an interaction, each new object you interact with brings with it an unknown phase. So now we have to rely on probability to deal with this inherent uncertainty properly. Our ignorance of phase is uniformly distributed, so we can assign a prior probability to the phase, 1 over 2 pi. And to obtain a likelihood of a given outcome, which is what we're computing when we do quantum mechanics, we must marginalize over all of the unknown parameters, which are all of the unknown phases in the interactions. And if we perform this marginalization, you see that we are basically summing modulus squared quantities. And this is really why quantum mechanics is a probabilistic theory. And the likelihood is additive because of the scalar sum rule, and it depends on the modulus squared, which is the Born rule. So you can show that all of these things arise from these simple symmetries. So here you can see, here it looks like the foundation of quantum theory is pretty elementary and simple. Quantity and uncertainty fused together into complex numbers with uncertainty really referring to phase. And the observable quantity is the modulus squared, which is the Born rule for arbitrary amount. And that represents ensemble averages, which is what the experimenter measures. So we have that. What's nice about this is quantum mechanics and probability theory are derived from the same symmetries. They can't possibly contradict one another for that reason. And in physics, we make predictions which are quantified probabilistically in terms of likelihoods. And so given those likelihoods, Bayesian analysis then computes posterior probabilities, which assess the models in light of the outcomes that are actually observed. And that is the relationship between quantum mechanics and Bayesian inference. Quantum mechanics deals with computing likelihoods, and likelihoods are used in performing inference. So now we can go a bit further and see how the multiplication rule B comes into play. These three different rules are potentially going to be used to describe different types of interactions. And so rule A, multiplication rule A we see is used in quantum mechanics. What is B good for? Well, B, because these are all possible descriptions, we can then ask what could we possibly describe with B or C? They're going to be consistent with the symmetry, so they would be good descriptions of something. And I'll look into that briefly here. So here we can consider objects that can exist in two states, let's say up and down. This gives us a quantification consisting of a pair of complex numbers, basically using the rules A, the multiplication rule A, and we'll have pairs of complex numbers now. And qubits, we'll call these qubits, will obey associative distributivity. So the representation is two-dimensional over the complex field. And these generators, these generators that we have will give us the Pauli matrices. So B, the generator for multiplication rule B, gives you sigma x. I times the generator for multiplication rule A gives you sigma y, and then together B times A gives you sigma z. So these are the Pauli matrices. And so the multiplication rules A and B together give you the concept of spin. And we see that we get the scalar quantifications come from these different, these three Pauli matrices. And this gives us a relationship between these new quantifications that we can construct from these operators. And this is really the first clue that 3+1 spacetime emerges from quantum mechanics. So with complex coefficients, these generators define the 6-parameter Lorentz group, under which ensemble averages of independent samples results in this relationship, which is invariant, or this quantity, which is invariant. So if I go back to those original multiplication rules, these two here together basically give us a 6-parameter Lorentz group. So we can see that when you think of these multiplication rules as being constraints that constrain your description of things, you can see that the descriptions we use in physics are actually coming from these constraints, and they ought to be. It gives you the possibility of deriving physics, which is quite interesting. One could have potentially derived physics before encountering the physical world, which is quite a thought when you imagine that the physical laws are somehow laws dictated by Mother Nature. If you think of the physical laws as being constraint equations that constrain any attempts at quantifying physical things, then it's not so surprising. So the shift in perspective on what you mean by a physical law gives you a great deal of freedom. So we now have these symmetries of associativity, commutativity, and associative distributivity, along with the consideration of uncertainty, give us the basic mathematical descriptions of the universe. We get from this, you can get the quantum mechanics as a probabilistic theory. The Pauli matrices and spin derive from multiplication rules A and B. This also gives you concepts of energy and momentum and phase and action. And from that, you can then integrate using rule C, which I don't have a slide for. I should have made that. I didn't want this to take too long. And you can see that operator C is an integrator. I'll go back to that. Here we go. So here's operator C. If you imagine multiplying it times something like dt on the top and then t0 down below, you can see that this is going to basically integrate phase. So time, it comes about from integrating phase. And this basically allows you to integrate time, which then when combined with the other two, allow you to integrate, you can integrate phase up to obtain time, and you can integrate momentum in the other two up to obtaining positions. So it works backwards from what we're used to. What we're used to is we start out with wave functions and we have positions and times, and we take derivatives to obtain energy and momentum, which are supposedly more fundamental. So we basically work backwards in the traditional way. We start out with something higher level, position and momentum, or position and time, and we take derivatives to get momentum and energy. This is actually going from the ground up, which is what I think would be a better foundation. That's how you build things, from the bottom up. So here, basically, we have energy and momentum and phase coming in from the beginning. And then with operator C, you can then integrate that to getting a three-dimensional space-time. And that comes out as an integral of phase and energy and momentum. So this is the direction our work has taken. And and why does mathematics work? Which is a question that's always had me wonder. Here it's easy to see the symmetries. These symmetries constrain our mathematical description of physics, which is why it works. And that's why it's derivable, which is interesting. The universes can't just do anything. As long as you have these symmetries hold, then your description of systems or interactions that obey these symmetries are going to have to follow these mathematics. And that basically is the theorem. So here's one of our most recent papers on this. So I hope you enjoy that, and thank you.
Okay, thank you very much, Kevin, for this nice talk. The people who want to make a question or a comment can indicate it in the chat. I have a little question.
Yeah.
Do you think that this analysis can be replicated in another physical theories that use another type of space or space-time, like string theory or this kind of things?
Oh, I didn't quite follow that. I'm sorry. The connection wasn't so good for me.
Ah, sorry.
Sorry.
Do you think that this analysis can be replicated in another theories that use another kind of space-times, like in the string theories or this kind of?
No, that's a good question. And that's basically where we're headed with this, is we want to see it from what we have so far. It looks like these symmetries allow you to generate space-time as integrals of quantity, more fundamental quantities like phase and energy and momentum. And so we want to look into that to see if you can build space-time up from that foundation. And if you build space-time that way, if you can do that, then it's going to automatically be consistent with quantum theory. So we would have a theory of space-time that's consistent with quantum mechanics from the get-go, which is really how you would want it.
There is a question from Federico Holly.
Hi, Kevin. Thanks for this from this talk. Yeah, it's great. So I wanted to know what's your take on photons, because you mentioned that when you count atoms and molecules, well, that the counting, it depends on the level of description that you are taking, right? But then if I have a laser, an attenuated laser, and you prepare a coherent state, then you will have a superposition of different numbers of photons. So you don't have a definite particle number. So what will be your take in that situation? How many photons do I have? Or photons in that case will not be real entities, and only the quantum field? What will be your take?
Well, that's a really good question. That's something I hadn't considered. If additivity doesn't work, then you've violated one of those four conditions, and it would be, and that would be my first guess. And then so then the question would be which of the conditions are violated in that situation. So, so in the case where I combine butane molecules with oxygen molecules, the condition that's violated is that of closure. So it's hard to imagine that you're going to have a problem with closure when combining photons. So yes, I'm curious about this. I'll have to think about that.
Mhm.
Thank you.
Thanks.
That's a very good question.
Thanks.
Okay, we are in time, so thank you, Kevin, again.
Okay, thank you so much.